This block will be about causal discovery, which is a slightly different twist or different field. It's not exactly causal inference, but highly connected, I would say. Actually, that's how I perceive the two. And I won't tell you exactly what it is. I'll let the speaker do this. And we'll have two speakers, and we'll start with the non-technical introduction to causal discovery with Professor Martin Huber, who is also a top researcher in causal inference, highly respected. He wrote and published two books on causal inference, which are particularly useful probably for this audience. The last one, impact evaluation in firms and organization. And actually, during the giveaway later during this event, you will be able to win one copy of Impact Evaluation in Firms and Organizations. So now we are going to listen indeed to Professor Martin Huber from the University of Fribourg about this non-technical introduction to causal discovery.
Yeah, thank you very much, Quentin, for organizing this great event and also for inviting me as a speaker. So as already mentioned, this is an introduction to causal discovery. And I just want to contrast this again to the previous block on impact evaluation. There we have seen some good examples about impact evaluation and causal inference, where the idea is to assess the effect of a predefined cause on an outcome of interest. So for example, what is the causal effect of a marketing campaign on sales? Now in causal discovery, instead, we want to learn a system of causal relationships among multiple variables. Okay, so we don't have one variable we interfere on, so one intervention like a marketing campaign and one key performance indicator like sales, on which we want to assess the effect of a marketing campaign. But we have multiple variables, for example, the marketing campaign, consumer attitudes, location, and they might have effects on each other, or they might have joint effects on some outcome variable or key performance indicator like sales. And what we want to do is we want to learn these causal relationships, right? So causal inference focuses on one specific effect, but causal discovery aims to learn the causal structure in a system of variables. And one key concept in this context is the so-called deseparation criterion. And this is a criterion which links the presence or absence of the statistical association between certain variables to causal associations between those variables, right? So I try to make this clear by means of an example. If you take a look at this first causal model here, you see that the marketing campaign has an impact on sales, but actually the impact of the marketing campaign works through changing the awareness of a product. Okay, the awareness among customers about the product. And after this has changed the awareness about the product, that in turn might increase sales. Okay, so what that means is we have actually, through the causal effect of the campaign on the awareness and of awareness on sales, we have a statistical association between the campaign and the sales, right? So people who are exposed to the campaign buy on average more than people who are not exposed to the campaign. But as the effect runs entirely through awareness, what that means is if we control for awareness, so if we only take people that have the same level of awareness, then we actually find no longer any statistical association between the campaign and the sales. So among people who have the same level of awareness, there is no longer any association of being exposed to the campaign or not with the sales, because the effect entirely runs through the awareness, right? So that means actually the awareness blocks any causal effect of campaign on sales, right? So in terms of statistical independence notation, means that originally there is an association between campaign and sales. But if we only take people with the same level in X, in awareness, there is no association anymore, and this inverted T means here there is no statistical association. As a second example, you could also have that actually the campaign does not have an effect on sales at all, but it could be that the awareness has an effect on sales, and the awareness also has an effect on whether someone is exposed to the marketing campaign or not, right? Because people with a higher product awareness might be more likely to visit a shop, and in the shop they are more likely to be exposed to the marketing campaign. So here we still have a statistical association between the marketing campaign and sales, but there is actually no causal effect. The statistical association only comes through something that we call confounding, namely the people who are exposed to the marketing campaign are different in terms of their awareness than the people who are not exposed. Okay. So again, here we have no causal effect, but we still have a statistical association between the campaign and sales. But again, if we only compare individuals with the same level of awareness, there is no longer any confounding, right? And any statistical association for this reason. So you see these two models are different, but they have the same implication in terms of statistical associations between campaign and sales. That means multiple causal models can give us the same statistical association. So what we finally have is we have a structure where actually the campaign affects the awareness, but actually it's now the sales that also affect awareness. So customers who previously bought the product, right, their awareness is changed, right? So here is again no causal effect of sales on or there's no causal effect on the marketing campaign on sales, right? And in this case, actually, originally, the campaign does not have any statistical association with sales. But now what happens, if I only compare individuals with the same level of awareness, I suddenly introduce a statistical association between the campaign and the sales. Because if people have the same level of awareness, it could either be that they have been exposed to a marketing campaign, and then they might have bought less in the past, but they have this level of awareness because they have been exposed to the marketing campaign. Or if they have not been exposed to the marketing campaign, their same level of awareness is obtained because they bought more of our product in the past, right? So this is what is called the collider structure. And if this was a little bit fast now, the important takeaway is that, well, you can have structures with statistical associations, right, where it's not fully clear which causal structure drives that statistical association, right? And so learning causal discovery, so learning causal associations between multiple variables relies on these different basic structures. And what that means is, if we aim for a causal discovery, it could have that a certain pattern of statistical associations or no statistical association is actually given or consistent with multiple causal models, right? So, for example, if we observe that some variable D is associated with some outcome variable Y, but is not associated after we control for X, right? It could either be that we have a causal chain in the direction of D affecting X and X affecting Y. We could even have the opposite, like Y affecting X and X affecting D. And we can not distinguish these two models based on the statistical associations. Or we could have this confounding case even that we have seen before, that X affects both D and Y, okay? So we cannot uniquely identify a causal model based on these statistical associations because we have these three possible causal structures. There are, however, cases where we can actually uniquely identify a causal model. And this is when we have the collider structure, right? So if we have this case that we have seen here before, if the campaign affects awareness and also previous sales affects awareness, and we learned that these two variables are not associated with each other originally, but are if we compare individuals that have the same awareness level, then we know actually that we have exactly this causal structure. In any other cases, we don't know this. And so very often causal discovery is a very tough goal in practice. And we can improve sometimes in terms of finding a more likely causal model by using domain knowledge. So maybe we know that, for example, the causal chain can only go in one direction, but not in the other one. Or also having experimental data where we can explicitly investigate the causal effects of some variables in our system, or also having temporal ordering, because we know, for example, that marketing in the past can only affect the sales outcome in the future, but not the other way around, right? But very often in causal discovery, the problem remains that we cannot uniquely identify the underlying causal structure. And that's what we call a Markov equivalence, right? So we could have multiple causal models that are consistent with the associations that we find in our data set. Nevertheless, there are maybe somewhat more narrow problems where causal discovery can still be very useful, right? So for example, rather than saying that we want to learn all possible causal effects in a system of variables, we could say maybe we only want to learn all the variables that directly affect a key performance indicator of interest, right? So and this is a more moderate goal, but still an interesting one, right? So we ask ourselves, which variables directly drive the outcome, for example, the sales outcome? And here there are actually algorithms that iteratively try to find this out in the following way, right? So here we can have multiple variables that have a direct effect on sales. So for example, again, the marketing campaign, but also previous awareness about the product, right? And it could even be that these direct effects have some effects among each other. And then there could also be indirect variables, so variables that only affect, for example, the marketing campaign, but do not directly affect the sales outcome, okay? And now under certain assumptions, namely, if we observe all the confounders that jointly affect our variables, which we want to assess in terms of their direct effects and the outcome of interest, then what we can do is we can run iteratively some kind of analysis of the direct effects of the different candidate variables that we have to find all the variables that have really a direct effect on the sales outcome of interest, right? And we need to impose some assumptions, but under these assumptions, there are algorithms which can deliver this. Then a goal related to this, but maybe under slightly different contexts, is the context of assessing causal invariance. And here we have again a set of possible variables where we think they could have a direct effect on the outcome. But now what we want to do is we want to assess whether their causal effect is actually stable across different environments that we have. And different environments means, for example, that we could run this causal analysis across different regions or across different time periods or across different product markets, right? So intuitively, what we try to do is we try to assess, for example, the effect of a marketing campaign or also the effect of awareness on our sales outcome. But we have different environments, so different times or different regions or markets in which, for example, the share of people exposed and not exposed to the marketing campaign differs. And so that's meant by this error of the environment Z, so a different market, for example, on D, meaning that across different markets, we could have different shares of people that are exposed to the marketing campaign. If we always find a stable effect, right? So if the effect does not change across these different environments of the marketing campaign on the sales outcome, that actually means that we have no effect heterogeneity, so the effects remain the same across different environments. And it also means that we have no confounding variables, so other variables which actually bias or contaminate the estimated effect. Okay. So in a very short wrap up, what we can do when we consider causal discovery. We can aim at learning systems of causal relationships among multiple variables. And I've mentioned that this is not an easy task. It's a way more sophisticated and also difficult task than just running an A/B test, for example, right? But we can exploit specific statistical patterns to at least boil down a large set of possible causal models to a smaller set of causal models that is consistent with the patterns that we see in our data. In addition, if we are interested in more narrow tasks, so for example, finding all the variables that have a direct effect on our key performance indicator, then we have specific algorithms tailored to this. And here the chances that we get actually more narrowly defined causal model are then actually higher than if we just try to learn all the possible causal associations. And if you're interested in the details of this, because 15 minutes is not much to discuss all of this, right? Then you can take a look at my survey article, which is freely available. So it's open access, an introduction to causal discovery. So yeah, thanks a lot for the attention. And I have, I think, managed to almost stay within the 15 minutes. Happy to discuss more questions if there are any.
Thank you very much, Martin. That was a great introduction. And indeed, I shared in the chat the link to your valuable article and introduction to causal discovery. So I'll relay, depending on the time it will take to answer, a few questions from the audience. One is actually connected directly to this, which is question in marketing often involve many variables. And so basically it makes DAGs and proper causal modeling difficult at scale. And do you think, for example, causal inference is something that might help you to solve this problem when you start writing down the many potential variables that you should take into account? And do you see this in practice as a tool that can help to resolve this uncertainty?
Yes, exactly. I think the most important thing in the beginning is really to write down the causal model, and it's actually better to do it graphically because one sees the possible connections directly, right? So writing, so actually drawing a causal graph, right, is very helpful. And then depending on what you actually want to assess, you either go for the assessment of a specific causal effect. Even then you need to know the causal links of different variables, right, to understand which variables you need to control for. Or if you really want to learn several causal links between different variables in your system, then you need to go for causal discovery algorithms. But also there you can put some constraints if there is some domain knowledge, right? So depending on how big your problem is in terms of what you want to identify causally, it's more or less challenging to do so. Yeah.
And a very question also from the audience, acyclicity. In practice, basically, you often have cycles, right? In particular, if I think about when I was in academia, my research project all suffered from simultaneity of reverse causation, which is directly a cycle. And how do you see this in practice? How do you solve this potential limitation? Why do we need basically this assumption sometime?
Yes. So if you have cycles, right, then you have feedback processes of the outcome on the variable of which you want to assess the causal effect, which we call the intervention or treatment variable. And then the first question is it really a cycle, or is it just that the past outcome affects the treatment, right? If it's the past sales that affects the marketing campaign, you can still control for past sales. But actually, in market equilibria, we very often have this simultaneity problem. And then one possible solution is to use instrumental variables if you have good instruments. Instruments are variables that only shift, for example, the intervention variable, so for example, the price policy, but not the outcome directly, right? But then there is no straightforward solution directly. It depends on the variables you have available in your data. Yeah.
Thank you very much. And there is this notion of time, exactly as you pointed. So I just put also in the chat a reference, which is sometimes you draw the arrows and you see a cycle, but actually you can break the cycle if you have data that are granular enough, because as you said, it might be not simultaneous, it's in the past, and hence then it can break these cycles. So there is a nice reference that I just shared. Martin, thanks a lot